language I will use is clean, which is, well, Haskell-ish, or you could also say Haskell is cleanish, because they have, well, similar languages. And this task-oriented programming is actually, well, a style of functional programming. Actually, it's a style of functional programming which we offer by a library, a huge library, which you can use to program things for the web. I will show you later what it offers and what you can do with it. And we use it for constructing real-world applications, and I will tell you the application later on in more detail. But basically, it's a vessel tracking application. So it's been used for worldwide observation of vessels. So there are many vessels, and I will show you later on. And perhaps you want to know who the vessels are and what they are doing. So you can click on, you have a kind of map of the world. And you can click on one of the icons representing vessels. And then it shows you what the vessel is and what it has been doing. I will explain later on why you want to do this and why this is, not so an easy application to make. But anyhow, it's completely written in a pure functional language, in clean. It's between 100 and 150,000 lines of code. So it's I think, a real-world application. And it's a multi-user one. So several people at the same time play with this application to investigate what's going on in the world on the area of vessels. So what I will do is first talk a little bit about clean, and then about task-oriented programming, and then I will explain a bit about this application. So, clean is very similar to Haskell. And actually, the reason is that I think both Haskell and clean are inspired by David Turner. So this afternoon, there's a special session to memorize David Turner and his wonderful work he did. Well, for me, at least, it was a life-changing experience when I read his paper. So that was in the early 80s, late 70s, that he wrote some magnificent paper about, elegant notation to replace the Lambda calculus, this nice layout-free notation where you have, or layout-sensitive notation, where you have algebraic data types, list comprehensions. Well, for me, it was beautiful to see. I was a C hacker in the past, and then when I saw the notation, I think, oh, this is nice, mathematical based. I was really, it changed my life. And then I also saw the implementation he proposed using combinatory logic. And it was even beautiful. So it was old school mathematics, and I really, really, really loved it. So for me, it changed my world. So I digged into this functional programming. And we also started then to do a project where actually the work on clean was started. And of course, it was beautiful what David has done, but there are also, room for improvements. There's always room for improvements. So we started to work on clean. It was in particular, what we wanted to have is a fast code. Because it was nice what David did, but clearly it was not as efficient as, let's say, writing a program in C. So we worked on that. We wanted to change that. And there were also some problems with, how to do, interaction, how to do I/O. That was not clear at that moment as well. So we started this project, and I was very fortunate when we started this project, because I worked with very nice, but also very knowledge people like Henk Barendrecht, who he wrote the standard book on Lambda calculus. Is now called the Old Testament. A decade ago, he wrote the New Testament, as we call it, which is on the type Lambda calculus. And together with Henk Barendrecht and Jan Willem Klap, who is, Mr. Rewrite System, and people from East Anglia, Ronald Sleep and Richard Kennaway, we thought about what the semantics, the proper semantics of, well, what we think functional programming should be. And together we came up with the idea of term graph rewriting, which actually explains how to rewrite a function in such a way that you maintain sharing. Because if you have a pure language, well, there are no side effects. And since there are no side effects, you can calculate the expressions at any moment. But then it's good to retain the sharing, because you don't want to calculate things twice, because you know, well, the result will be the same anyway. So actually, this term graph rewriting explains how to rewrite a function. So we also did an implementation quite soon afterwards. The first implementation was made in Modular 2, and you can read the paper at FPCA. And of course, we want to have an implementation of clean in clean, and we used the first version as a bootstrapping device to make an implementation in clean. So I will now pinpoint to some peculiarities of clean. Well, first of all, clean is known from the uniqueness typing. So if you want to do, let's say, I/O, or you want to update an array, or well, do the things well you need to do dealing with a not functional world, then you can use uniqueness typing. So, for instance, a standard function in the library is something like write a character to a file, and you can see this mark in this file, which is the uniqueness mark. It is a type attribute, and it tells you that this function wants this file to be unique, and that means that it's not shared. So this knowledge of sharing and not sharing fits perfectly in this term graph rewriting world. So since the file is unique, and the type system guarantees that it's not shared, well, then you can use this file as you get as an argument to construct a result. And that actually means you can simply update a thing. So uniqueness typing is very handy and used a lot when you write down clean programs. Some people say that it's a kind of linear system, but it's actually not, because it's allowed in a function body to share things, to share unique arguments you got. So if you share unique arguments, well, they become non-unique, but they still have a purpose, because, for instance, you want to read from a file, and then the file doesn't need to be unique. It can be non-unique, because reading is not a side effect. And also, other thing is that the type system is polymorphic in the unicity. So, and it's an inferencing system. So what you can do with that is that it means that you can reuse the functions we all love, like map or append. So all the library functions can be reused, because it's polymorphically attributed in a unicity. That means that, well, if you use it standard with non-unique things, it will work. And if you use it with unique stuff, it will propagate the information of the unicity, so that you can use it whatever you want. Of course, you get a lot of type errors if you share unique stuff in a context, or share unique stuff in a context where it's demanded to be unique. Another thing we use in this application is the type dynamic. So standard you use, well, everything is statically typed, but sometimes it's very convenient to have a dynamically typed language as well. So in Clean you can do both things, and an example of this thing is dynamic apply, where, well, this is a function with 3 arguments. The first 2 are dynamic, and what actually it states is, okay, I have 2 dynamics, and dynamics are, let's say, pairs of values and types, and you do here pattern matching on these values and types. So it says, well, if the first thing is a function from A to B, and the second dynamic is something of type A, then I can apply this this function on this argument, and then what happens is that a dynamic type unification takes place of these 2 dynamics. The result should be here of type B, and the type B is here from static type. So this B with this carrots actually says, I mean here the B which is in the statically typed world. So in other words, this dynamic apply will only apply this function to this argument if it's dynamically unifiable and the result is of the type B demanded from the static world. So if the static world, let's say you apply this thing in a context where you want to have a Boolean out of it, then this thing will only be applied to each other if a Boolean comes out of it. And if not, it uses the default value. Finally, a thing which is there is, of course, dynamic types and dynamic programming. And the difference with a language of Haskell is it's built in the system. So the compiler knows when you define generic functions. So generic functions you can define with a sum of product type of approach. And if you do that, you can let a system derive, let's say, for instance, equality of what you want for your specific types. The advantage of having this thing built into the language is that the compiler will try to remove the generic overhead which is caused by using such a constructions. So I already used a couple of times the terms efficiency. Well, if you use the clean compiler, you'll see that you'll notice two things. First of all, is fast compilation. So it can compile itself, which is about 80,000 lines of code in a couple of seconds. And it compiles it from clean code to an abstract machine code. And then you need a code generator and a linker to get the application out of it. And it's very efficient, so the resulting code. And that's done by avoiding this term graph rewriting. So in the semantics it's important, but in the implementation you try to avoid using it and use as much as can of the standard machinery. Because it was that fast, we didn't need to have an interpreter for a long time. So only a couple of years ago, no, already 5 years ago, we made a clean interpreter. And the idea is that well, nowadays we have browsers. So wouldn't it be a cool idea to, execute clean code in the browser? Well, and then you need a kind of interpreter because code generation for a browser is not a thing to do. So, well, that has been made in the 19th by Camille Stubbs. And, well, since it's an interpreter and we have a version in C, you can run it on any machine. Well, to go to the browser-like application, what's important there that you can have code running on a server, which is then probably compiled code because that's first faster than interpreter code. And you can have code on the client, for instance in the browser, which is then interpreted. And the important thing is that you can send closures from one to the other. So the server can decide that something has to be calculated in the browser, and it can send then the closure, which is a serialized term graph, to the browser. And assuming that the browser has this code available, it can calculate it. And they can, exchange information whenever they like. Does it make sense, what I'm saying? Okay. So this is, well, some highlights of Clean, which we will use in this application. Then I will talk to you a little bit about task-oriented programming. Well, once we had this nice efficiency, and we can do all these things, we came to on the idea that well, it would be nice if you write down applications, for instance, for the browser, for multi-user applications where people work together on the internet, that you need some kind of support for doing that. And so we came with the idea of task-oriented programming, where you organize your functional program in such a way that you think about what does this program has to do. So the idea was that you focus on the task people and machines have to do, and you try to describe this as accurate as possible and as close as possible into your code, and try to do as much as you can automatically. So generate as much as you can automatically, such that you can focus on what does the program has to do, instead of how technically you can realize this. And task-oriented is, in that sense, a good idea because, well, people do tasks and machines do tasks. So why not have this notion of task as a central part of your code? So if you look at a task-oriented program, you see immediately, oh, this is what a program is supposed to do. And the technical realization is, well, done as automatically as much as possible. I will show you what this task-oriented programming means later on. But to realize this, we made a library. It's about 40,000 lines of clean code, which has an embedded domain-specific language, such that you can write down the application in terms of tasks. And then if you compile your program, it generates a kind of distributed task coordination system, which can run on several machines, such that people, when they work together, automatically the information goes from one user to the other. So from one clean source, we generate code for the servers, for the clients, and even for the Internet of Things thingies, devices. So the first idea of this thing was published in 2007, but we're now running the 4th edition of the thing, so we did a lot of improvement. You're never happy with what you have. And the 5th is on the way. Hopefully we can use that very soon. Okay, well, I will explain you what task-oriented programming is in a minute, but there are some other implementations lying around as well. So let me see. What is this idea about task-oriented programming? Well, first of all, what you do is you think about the domain. So if we think about the vessels and the tracks, what you do is, well, traditional functional programming. You think about the domain, make data types, make functions that access these data. So this is more or less standard way of working. So what then the next step is you think about the task. So what does the program have to support? What does people have to do, and how can I express this in my application? So it's a kind of workflow definitions where you define how all things are connected. Then we use this task definitions to generate the user interface. So from the task to do, we know that people have to do certain things, so we provide them with the interface for, well, doing their work. Now you can imagine that tasks people have to do somehow is connected to each other. So what I do will probably have influence to what you are doing. So these tasks have some connection, but you also need a kind of, global type of information sources. And that's where the shared data sources come in place. So the shared data source stands for information you want to share between all people working on the application. And underneath the carpet, there's a kind of a public subscribe system, which will see and will calculate which of the users is needing which type of information, and will automatically provide the end users with the information needed for doing the work. So if you compare task-oriented programming with functional programming, then you can, see the following. So with functional programming, you have a function, it has one result, you have function applications to combine these things. You can have higher order functions. Well, in a task, you have something which is of a kind of abstract type, task of A. And the special thing about this task of A is, where A can be any type, is that it's observable. So you can look at it as this value of A changes over time. It reflects the state of the work that is taking place, and it changes over time such that other people can see how your work is proceeding. And, well, of course, you want to combine tasks to making new tasks, so you have task combinators, you have higher order tasks, and so on. Well, from this task of A, we can generate then a graphical user interface from the types. And again, you want, well, perhaps you want to make this graphical user interface look in a particular way. So there are all kinds of ways to make it look like you want. And this, well, shared data sources are, well, used for communication and synchronization of data between the end users. Time for an example. So let's first look at well, what tasks are doing. So a task is actually a function taking a special context, which we call the iTask context, and a couple of well, arguments to produce something of task of A. In clean, we will write it down like this. So this is then what the thing is doing. So instead of one result, well, it gives you a result that changes over time. So the idea is, for instance, if you write down a paper, let's say. So in the beginning you have nothing. And then you work on it, and every time the content will change. Perhaps you don't like it at all, you start all over again. And some papers finish up, probably because there's a deadline. Because, well, before that it won't go. So not all tasks end up in stable tasks, but some of them do. So you might think it's a little bit strange that things change over time. How can this be done in a pure functional world? Well, it works because, well, in the implementation under the carpet, this particular function does not only returns a value, it also returns a continuation, the remaining tasks to do. And the system will automatically invoke the remaining tasks to do whenever something is changed. So from the outside, it looks as the thing is changing over time. From the inside, it's a kind of recursion that takes place each time a task has made a little bit process. So this value changes over time, can be any time, can be higher order, for instance. So a task may deliver a task which you want to give to somebody else. And, well, it can be observed by others. So let's have a concrete example of a very, very simple task you can do. So on the top you see a definition of a record type. It's the type family, where you have a person which may be married and they might have a couple of children, and the person has a name, a gender, and the gender is, well, this is an old-fashioned example. It's only male and female. But you can extend it in that way. So the task of we are going to do is simply fill in something of this type. So simply to fill in a family. And for that we have a basic task which you can use. It's called enter information, and that is good enough to produce something, a user interface to fill in a family. Well, there needs some boilerplate code. We need to have a start rule. And we need to import this iTask library and derive the class iTask for the thing. But that's basically all you have to do. And what then you get, if you go to the browser, you get a form to fill in a family. Like you see immediately the correspondence between the algebraic data type and this form. Or if you don't like to, you can always change this thing to make it look differently. So you can fill in the thing, and you see, for instance, the type maybe person is turned into a Boolean, and if you then click on the Boolean, you can fill in your partner, and then, well, you can fill in the children, and so on, and so on. If there's enough room in on your screen, you can fill in a nice family tree. So this whole thing is only depending on, on the type. So if you want to do the same thing for your, algebraic data type, you simply define your algebraic data type, do the derived class of the iTask for your data type, and you're in business. You can do what you want. So this is nice because you don't have to think about the user interface. You simply think, oh, this is the type it has to provide, and then then automatically this thing is generated using this generic mechanism. Does it make sense? Still, people puzzled? Yeah, okay. Now that's fine. Oh yeah, by the way, you see here that things are changing because every time you fill around with the form, things are changing, right? Now let's think about that you want to have some context restriction on it. Suppose that you want to have, let's say, a form to filling a palindrome. So it's not it's a task of string, but it's a string which has a certain property. So how would you do that? Here this observation comes in. So what you can say is, okay, I want some information. It's of type string, but looking at this type string, I want to have some predicates on it. So, for instance, if it's a palindrome, then it's fine. I return just a v, so that this task has type maybe string. But if it's not a palindrome, I can always say cancel, and then I'll cancel it, and it will turn nothing. So So what happens is that you have a predicate, and automatically also buttons are generated, and the activation of the buttons are only it's only possible to hit OK if indeed the string you create is a palindrome. Yeah. So a couple of things happen here. Things are generated, things are observed because it is being observed what you type in. And buttons are active or non-active depending on predicates hold. So in general, it works as follows. You have this we call this a step combinator. So there's a task of A going on, and this value of this task is changing over time. And then you can specify a list of task continuations, which looks at the A and produces a B. And what we can define is buttons. You can define predicates. It can be the clock, so it can be that the time is over and it's done. You can raise exceptions and so on. So all of these things can be done just observing what people are doing. Make sense? This is a kind of sequential thingy, but you can also have a parallel thing. So you can generate a lot of parallel tasks going on, producing something of type A, and the whole thing then produces something of type list of A. And again, everything can be observed. So a task can observe how the progress is of some other parallel task taking place. And that's important to have because you perhaps want to stop if some other task already has found a solution. You might upscale, you might downscale the number of tasks going on. So this parallel thing is a very powerful Swiss Army knife type of thing. There was a paper of Bas Lijns just about what this parallel task combinator can do. So, With this system, you have a library with basic tasks where you can enter information or just show information. You can combine things in a sequential way. You can combine things in a parallel way. You can change the layout. And last but not least important, you can assign tasks to people. Because you want, people to do things. And a special operator is for that. Before I give another example, I go to the shared data sources. So, you have the sequential combinator, you have the parallel combinator, and they can look at what's going on. But it's also very convenient to have, let's say, global information you want to share between the people working on the system. And what we've done is we defined one abstraction layer for all types of shared data you can imagine. So for shared memories, for files, for the cloud, for time, and for sensors. There's one interface. What you then can do in your code, you can, for instance, write to a shared memory. If you write to a shared memory, then, this information is changed. And then the system will automatically see who is using this thing, who is depending on this information, which of the tasks want this. And then there's this publish subscribe system which automatically notifies the tasks that something is changed where they depend on. And again, there are combinators to combine all these things. We'll skip that. Okay. Small example, for instance, an example would be view the current time. This is a task of type task of time. And it uses this view chat information, a prompt, and the current time. The current time is predefined for you. And that means that what you get is, an image of the current time, and the current time will be ticking. So this is just a task. But each time the clock ticks, it sees, okay, there's 1 second, we are 1 second further, and apparently this task needs this information. So it gets a signal, it gets a new time, and it will show the new time. So just by writing this down, you will see, you have a clock. If you don't like the clock, the way it looks, you change it. Well, this then can be used to write on collaboration between people. For instance, this is a function where you have 2 users, user 1 and user 2, and they all get a prompt. And what happens here is for this particular type, which can be any type, a share is created, which will get a default value using the generic system. And then with the share, one person will be able to update the information, and the other person will just see the information. And in between this you see an operator for doing things in parallel. So, for instance, suppose that you want to play with a Google Map. You make an algebraic data type which reflects the information you want to see in a Google Map. And then by using this monitor walking function, what will happen is that a Google Map will be created, one for, let's say, Bob and one for Alice, where Bob can play with the Google Map, so shift it around, make markers, and Alice will automatically see what Bob is doing. Of course, with a time delay, but, So, and the reason is that they share this information, and the public subscribe system will see that Bob is changing something. Then the value of the algebraic data type is changed, passed to Alice, and Alice is then showing what's going on. It will also work it works for any type. For instance, for this family tree, you could do the same thing. You just change the type for Google Map to family tree, and one then can, create a family tree, and the other will see what has been created at the same time. Okay, this gives you a little bit of, the machinery we have to do things. And once we had it, well, it would be nice to have real-world examples to see if you can use the thing. And one of my PhD students, Bas Lijnse, did a very nice job. So he worked at the Dutch Coast Guard for a period of time just to see how things are organized over there. So in this particular prototype, he coordinates the search and rescue activity of the Coast Guard. So the Netherlands is close to the North Sea, and you can have lots of wind and storms, and a lot of problems can happen when it's stormy weather, and people probably might have to be rescued from ships or platforms, or when they do a kite surfing or something like that. And that all has to be coordinated. So the helicopter guy knows how to rescue somebody from the ship. You don't have to tell him that. But you have to coordinate things. So what can be done, what cannot be done, what's allowed to be done. Perhaps hospitals have to be informed. So a lot of things have to be, organized. And actually that was a very nice real-life problem to express in a task-oriented way. And Bas did a really nice job at it. And we used a lot of his knowledge in the system to make it as flexible as it is right now. But, it stayed to a prototype. We never turned it into a real application. Partly because we were afraid, because this was such a new software. So we did not want lives to depend on, on this, new stuff. But actually, they were very happy with it, and they asked us to make another type of application, and that's what I will talk now. So this is not a prototype, but a real application made by Stefan Michels, who's also the co-founder of Top Software. So we created 5 years ago a company to make this, not an academic exercise, but a real thing. And the idea, is the following. So what is the problem we want to solve? Well, if you look at our waters, the oceans, the sea, the rivers, well, they are very important. Certainly in the Netherlands, where we are so close to the sea and where we have the Rotterdam harbor. So the waters are used for goods, transporting cargo, containers, but they're also important for energy. So nowadays there are a lot of wind turbines in the North Sea. There are electricity cables, there are gas pipes, and a lot of information. So the internet, there are a lot of cables connecting the Netherlands to other parts of the world. So we are kind of a central node in that. It's also very crowded. So worldwide, you have more than 150,000 vessels, which are large vessels. It's not the little boats, but the large ones. We have the North Sea with the Rotterdam harbor, which is one of the busiest harbors in the world. We have lots of windmill farms in the North Sea, and lots of glasvezel kites. Here you see a picture of these 150,000 vessels. Just a snapshot we made. Well, there are so many. If you need to zoom in to see something. Otherwise, you just see lots of icons. Here you see a picture of the Netherlands and the North Sea. The more red you see, the busier the route is taken for vessels. So there are many ships traveling around the North Sea. And you also see a lot of windmill farms, partly planned, but most of them are already there. So That's a kind of danger because the ships, go close to the windmill farms, and if it's stormy weather, then they might hit these windmill farms. So it's not a free waters anymore. You really have to, obey rules, otherwise dangerous things happen. Which did. So a year ago, one of the ships drifted away and went right into the windmill farms and hit some of the equipment. So it would be nice if you could detect this thing timely before this disaster happens. Also afterwards, you want to know things like when there is pollution. So when a ship loses oil or loses containers, you have to know, wow, who was that who lost the containers? Who can we blame? So all this type of information you want to use. Well, Rotterdam Harbor is a large one, and it's the Netherlands. So lots of drugs. So it's amazingly amount. Every day they find drugs. It's terrible. But it would be nice if you could detect it and prevent these things. We live in dangerous times, and you all, of course, know about this gas explosion that took place. But in the Netherlands, if you read the newspapers now on a daily basis, there is some news about the things that might happen and the things which are happening. So it's really getting very dangerous nowadays. And it's, imaginable that the infrastructure we have there will be destroyed. At least they are inspected on a daily basis to see where they are and what could have, what they could do. So this is really a problem. So it's not toying around, it's a serious business. So we need to know what's going on in these waters. So, and this is what this application do. It's called VIA, Vessel Information Integrating Application. Well, what's in the name? But what it does is it collects all types of information of the vessels. So each vessel should have a transponder on board to tell them who they are and where they are. And all this information then can be received by AES receivers. You can have them on shore, and you can have them on satellite. So these transponders don't have a big range. So if they are in the middle of the ocean, you cannot see it on shore. You need the satellites. But then the satellites are not always there. So you have kind of partial information. It's not total. Then you also have radar information or other type of information. Perhaps you have satellite images. So there's a lot of information you have about these positions. And in addition to that, you have a lot of static information. So who's the owner of a ship, which flag it is, what is the type of crew, what is the cargo. And this static information, as they call it, changes daily as well. Now, to monitor all this and to assign all this information to a particular vessel at a particular time is very difficult. So, because you cannot trust anything. So there might be wrong data being sent, but to be honest, they simply switch off the transponders so you cannot trust the information. It's also very easy to disguise yourself as a vessel to be another vessel. All things God has forbidden are possible and occur. So you cannot trust this information. And it's a lot of information. So what this application does, it finds all this information and stores it, unifies it, and stores it in a database. And you have to think about terabytes of memory and billions of data. It's a lot. And what you can do then with this application is to do queries, and you want to know what happens at a certain period of time in a certain area, and because everything is changing over time, you have to think very carefully. If you ask a question about the time matters then, because things change over time, and you can go back in time and see what is happening. So it's really a lot of information which has to be processed and done. And also that means that it's very difficult to focus on things. So what do you want to know? And what are you going to do then if you know these things? So you have to be able to focus on things. For instance, let's have a simple example where you have such a windmill farm. Well, there are all kinds of rules of entering such a windmill farms. Most of the ships, vessels are not allowed to enter, but some need to enter to maintain the stuff. Others are allowed to be in the neighborhood, but big vessels, and when there's windy, for instance, they are not allowed to be there because they can cause damage. So how can you then, you cannot look at it constantly. You want to have a way to be alerted if such a situation is happening. So what we did is we, again, defined a domain-specific language into Clean where they can specify the focus of interest. But then, of course, you cannot, these are end users, you cannot expect them to program things in a functional language. So what we did is we used this editor idea and the domenic types to give a structure editor to the end user. So it's, he or she can, then specify in a pull-down type of menu what things they are interested in. And the whole thing is type-safe. They say they cannot ask something which is not type-safe, but they can ask things which takes an enormous amount of time. So you have to be careful what you specify. And of course, it raises alerts on demand, such that they are notified on time, hopefully, that something is happening. So you can specify things which is a huge database which takes an enormous amount of time to calculate. So what we do is have a way to parallelize a query such that the database can be, in parallel, be asked to find out occurrences of this particular query. All right, so there are a lot of things to tell about this application, but I'm not allowed to tell you that. So it's non-academic, but I can't help that. So I told you what I can. So to conclude, using Clean and the iTask library, we've been able to specify this multi-user application. It is multi-user because people work together to find out what is going on and to do the things that have to be done if they found out that something is wrong. What I didn't mention is that we use our Clean version of a quick check, Gast, made by Peter Kommer, a lot. So what we do is every evening we generate everything from scratch. So the Clean compiler, the libraries, the applications, everything is generated from scratch every day. And then it goes through this property-based testing system for Peter. We have about 1,800 test cases and 100,000 tests each. And we do it every evening to see if everything is still working. Okay, that's, more or less what I had to say. So.
Okay, so we still have some time for Q&A. Do you have any questions? I see a question here. Okay, let's take one from the top first.
Hi, hello. I have a couple of questions, but let me choose one. So you said you had a lot of data sources, right? And those data sources are sometimes unclean, sometimes false, sometimes missing. How do you deal with that in practice? I assume you can't, like, it can't be a human looking at all of that data. There's just too much of it. So how do you figure this out?
Oh, okay. Do I understand the question? How do you figure out what was wrong and what is right, you mean?
To an extent, yeah. Like, if you have, let's say, conflicting sources of data for a position of a vessel, how do you decide which position to show, or do you not show?
We show the conflict, right? So if we see that there are multiple interpretations possible, then we show to the end user, well, you know, we notice that there are conflicts, and well, this is one solution, this is another solution, such that they can decide what is, well, might be the right, because we don't want to decide that for them, because they are the domain experts and they know which information can be trusted and not. So we'll show them then, well, these are the catalog of possible solutions we have. Is that fine? Okay.
Hi, thanks for the talk. You mentioned this dynamic typing in Clean. So based on the example, it seemed like it's more like a delayed static typing. Does it use the same unification algorithm as the static typing?
Okay, it is a kind, well, it is a delayed typing, you could say. But it is actually used for the situations where you want to store information of different type. So, for instance, if you have this public subscribe system, you need to have, well, a general way to store stuff. And since we are in a strongly typed environment, it's impossible to make such a storage without going to some dynamic type. So you will use that for such a storage, but in the context where you use the information, you know the type, normally. So this is a way for us to store information of general type, but we know that it's being used in a static context where the type is known. Does it make sense? Yeah. We also, at one point in time, had a possibility to do dynamic linking, such that you could store a dynamic to disk, and then another application could read in dynamic and decode, and then, but it was too much to maintain, so we stopped that for doing that. Yeah. Did I answer your question? Okay, thank you.
Any more questions? I see a question. Okay.
On the business side of it, were you approached by the Dutch Coast Guard to build the software, or did you have already an idea of something you could offer to them? Because I imagine there's a lot of domain knowledge that you need to know about this, right?
Can you please repeat? I did not understand the question.
Right, so I can see that your software is used by the Dutch Coast Guard. Mm-hmm. So I'm interested, did you approach them or with the software already there? Did you already somehow know what they needed, or did you?
Yeah, I understand. Well, what happened is that one of my PhD students worked at a defense academy, so we had good relations with the defense. But then, well, there was also a lot of secrets there. So he said, well, why not, go to the Dutch Coast Guard? They also have secrets, but not as many as we. They're a little bit more, easier to go. And that's, well, what we did. And then we made this first prototype, which was, I think, well, it was a very nice thing. In retrospect, I regret that we were not, turning this into a real thing. I think that they could be really, really happy with it. And then, another coincidence was that Stefan Michels, who's the co-founder of Top Software, he's really an expert in this area. So and then also expert in probability typed languages. So he really knows a lot of these things, and then it all came together. And yeah, did it answer the question? Okay, it is.
Actually, I have a follow-up to the dynamic typing question. On the slide, you showed that there was a fallback case with the underscores. So does the language enforce this? So does always when you specify dynamic types, you have to give a case to make the static type system happy?
No, it doesn't enforce that. What you could do is you can also have, let's say, you can create dynamics at any point. So if you get a result and you want to promote it to the dynamic type, you simply say, give me the dynamic of this thing. So basically what you could do is you can make a whole part of your language in a dynamically typed world with all the danger it has.
Of course, you get the runtime errors then.
Yes, yeah,
okay.
yeah.
Thank
so
you.
You have to be careful with that.
Yes, I had a question about Clean's compile times. I think you said 80,000 lines of code in 10 seconds or so. I mean, that sounds like a really good number. And I was wondering, is this like due to any specific property of Clean that makes it like, I don't know, it sounds fast, possibly faster than Haskell. So I was wondering if there's any, yeah, you know what I'm talking about, right? It's,
yeah, well, first of all, we have a guy who's very, keen on making things fast. Actually, when I want to, one of the Clean team wants to add something to the language, we first have to beg and convince him that it's useful. And the second thing, then we have to, you have to think about it if it's also implementable in the fast way. And otherwise, we have a problem. We have to, nag a long time before things are done in that way. But the basic thing is that the compiler is somebody says it makes coffee too. So it does a lot of things in one phase, which is for maintenance not so good, because the more phases you have, the better is it to maintain, but also the longer time it takes to compile. So we have it makes coffee 2 compiler, which therefore is very fast. But if you want to change something, you have to think very carefully, because yeah. So yeah.
okay, thank you.
Yeah.
I have a question. So you mentioned that the graphical user interfaces were mostly automatically derived. Is that correct?
Sorry, say it again.
So you mentioned that the graphical user interfaces, the GUIs, were mostly automatically generated, correct?
Oh, sorry, I can't understand you.
The graphical user interfaces,
yes,
those were mostly automatically derived, correct?
I still have problems with so the graphical user interfaces are generated by the types. Mm-hmm. And you can modify the way they look like in the way you want. Because the whole application I was talking about is all being generated. So all these icons, all these chips and things are being generated. And saves us a lot of time to program it, because there are hundreds and hundreds of properties of these vessels. And by just doing it once and for all, it saves an enormous amount of work.
Yeah, so the question that I have here is so you mentioned that you could adjust them if you needed to. So how much adjustments did you need on top of the automatically derived interfaces, and how much effort did it take compared to the rest of the application?
Okay, well, we had a lot of, let's say, improvements of how things should look like in the application. So the nice thing about it is you get something for free in the first place. So at least you can work. You can try things out and see if it does what it's supposed to do. And then you can, think about this layout improvements. But they're not very, you go to CSS and specify things. So it's not too difficult to do. I think the most difficult thing to do in the layout thing is that you have multiple users. So if you look at the code, you see all kinds of tasks being specified, and then some of these tasks are being assigned to someone. So you have to, go to this tree of tasks and figure out this is for this guy and this is for that girl, and then make it such that it looks nice. So there is some work there to do, but the system supports that. So it's yeah. It also has disadvantage that he's generating things, of course. But I think we are happy with that.
All right.
Hi, so I saw you present iTask in 2008, and it looked very similar to what you were presenting here. But of course, the big difference is that now you have this complicated system that's deployed in production. So my question is, what were the iTask levels, so like the infrastructure level or the library level changes that you've had to do since the 2008 era that were necessitated by this large application?
Do I understand you want to know what kind of changes we've made to the time in the iTask system?
Yeah.
Yeah. Well, in the first version I've published, we did not have the recursion under the carpet. So you did an explicit recursion. So if you did a task and you made a step, and then you simply recurse in that task to do the remaining thing. And that was not such a good idea because, well, you also have to think about generating this user interface. So if you do a recursive explicitly, then the question comes: for whom is this recursion intended? And now to have it under the carpet, it's clear that the recursion is intended for the task you describe, which makes it much easier for us to generate the user interface, because that also means that we only have to update the user interface because you're working on a particular thing. So that is one of the things we changed. Another thing, Mart is... where is Mart? Oh, there. Mart is currently working on is to have the type system, to change the type of the task a little bit, such that you can have tasks of which we know they can be ported to another machine without harm, and parts and tasks who use side effect structures, which you cannot that easily port to another machine. So we will change the type system, and hopefully it's ready very soon, such that it's more and more reliable in that sense. But these are the main changes I think we made.
Thanks.
Okay, hello. My question is also on user interface. So I wanted to ask, you've shown a lot of comprehensive things like Google Maps integration and different graphs and all this stuff. And my question is, are those built into language level, or you have some ways to, like, let's say you get additional requests from client to integrate YouTube video into application, right? And like show some like guide or instruction there this way, right? So is there a way and tools for developers to do it on application level, or you would go and extend language to support this?
Okay. So do you ask me if there's support for defining these?
Yes, yes.
Yeah,
how to introduce like such comprehensive UI things?
Well, I don't think we have support for that. So what happens if for any type you will get something, and with layout improvements, which I think is common HTML knowledge, you can then improve it. So for instance, for the Google Map kind of thing, you need to think about, okay, what kind of functionality of the Google Map I need. So you made an algebraic data type. It says, well, I have a map and perhaps a zoom factor or whatever, and you have flags, or whatever you are interested in. You define this in an algebraic data type. Then you make a mapping from the algebraic data type to the real Google machinery. And then when you, it has to go in two directions. So if you change something in the Google machinery, it's a task. So the underlying data value will be updated by the public subscribed machinery. And then you can make a new image of that.
So do I understand correctly that on application level you can define mapping between data and HTML structure, and then it works?
Yes. The update will go automatically. All communication takes place automatically. You don't have to think about that.
All right.
I will help my colleague.
Thank you, Rinus. I have another question about the dynamic typing. So the software that you're talking about here is a long-lived system, and something that happens to long-lived software is that it evolves, including the types. You might have a type, you might add a constructor, you might add fields to a constructor, but at the same time, because you have dynamic typing, you have values of the old types stored in your database. So you have a problem of updating the database when the types change. And I just wonder whether you have any smart ideas for helping deal with that.
I have no smart ideas, I'm afraid. So, but I hope everybody understood the question. So over time, things are changing. And this is a 24/7 application running. So if you change the application, and which we do very often because we are still working on it, there's a lot of additional wishes they have, the data types might change and the database. So then you have to migrate the database. And you have to, you really have to think very carefully about that. So I'm in for any smart solution solving this problem. But do you have one? No. So the only thing we can do is then modify the system and the code that has been.
If you change the type, does that mean that when you try and use it as a dynamic value, the dynamic match will fail, or do some matches still succeed if you change?
In terms of a dynamic, you mean, or?
Yes.
Good question. I don't think it matters. So it will survive the new incarnation. The problem holds with storing information in the real database, these terabytes of stuff. And so what we use is a database which is pretty much a functional language type of database. So it's not an ordinary database due to the speed we have to reach. But basically, it's a functional functional database. So it's a big tree where nothing is ever updated destructively. So that helps. So things remain safe. But of course, if things are changed, and you don't expect that, you have big problems. Yeah, better be careful. Any?
Okay, last question.
Thank you very much. So I like that talk very much. I liked your application. So I'm just in front of you, very close. Look down. Hello.
Sorry. Sorry.
Yeah, my question is, I like the fact you have information stored in the database with different validity or different confidence, and you can point that out when there's an inconsistency or a conflict. Did you think about adding the probabilities of, for example, accuracy or confidence in values? And if you did want to do that, could you do that within your type system? Because, of course, those probabilities would evolve.
Yes. Well, Stefan Michels is exactly, this is his territory, about probabilities and language which contain the notion of probability. But when we started this project, he thought it was a good idea to do it like that, even though we had all the expertise and all things. And the reason is, if you want to talk about probabilities, you also need data. So you need evidence that something is happening with a certain probability. And to obtain that evidence, that's not doable at this moment. So that's why we chosen not to, to assign probabilities to that, but instead of that, making clear that there is a conflict, and show the conflict, and then let the domain experts decide how to handle that. Okay? Did I answer your question?
Yeah, absolutely. Thanks.
Thank you.
Okay, so let's give a warm round of applause to Rinus.